All right, thank you so much for this opportunity. This is my first time being involved with these Alpha Chive procedures, and very happy to be here. My name is Brandon Creaston. I'm a postdoc at Argonne, and my research lies at this funny intersection between high energy physics, theory, hadronic structure, and machine learning. And so I'm going to just briefly give a snapshot of one of our recent projects and ideas that we've been working on. This is not all encompassing of everything I do, but this is just a little taste. So my research focuses a lot, or at least this talk will, around parton distribution functions. So PDFs effectively describe how a hadron's momentum is carried by its constituents. In this case, I'm going to consider the constituents as the quark species and the gluons. And you can see here in this plot that I show a representative example of a phenomenological fit of the parton distribution functions to world data. And you can see that they're shown as a function of the longitudinal momentum fraction x, ranging from essentially 0 to 1. And they're given at a particular factorization scale, in this case chosen to be 100 GeV. And now these parton distribution functions come to us through the language of QCD factorization theorems, which is the theoretical prescription which allows us to separate out the hard perturbative scatter from the non-perturbative matrix elements describing the hadronic structure. And so with this separation, we're allowed to define things such as parton distribution functions. And from this language, we're able to fit them phenomenologically to data. So example, neutral current Drell-Yan in PP to a final dilepton state here is one example. And now parton distribution functions are ubiquitous in collider phenomenology. Effectively, whenever we're using hadrons or colliding hadrons with leptons, we're going to need to use parton distribution functions to describe our data. And so they motivate studies relevant for current and future collider programs, such as the LHC and EIC, where one can think about Higgs channels, Higgs production channels, and gluon fusion, possibly non-standard interactions towards TT bar production, and even so much in DUNE, for instance, which is a neutrino program with neutrino nuclear scattering, for instance. And so we can't escape parton distribution functions. They're everywhere around us in high energy physics. And so what we want to do is build
Sorry,
a
Brendan.
sorry.
One question. One question. So what kind of processes are more sensitive to the PDF?
So are you talking about okay. So essentially, there are various different experimental pools that one can study on the PDF. It's hard to say a particular process is dependent. It's more or more dependent than another one. So that can be a tricky question. I think what's more interesting is how various processes pull on different regions of the X dependence of the PDF, for instance. So some experiments might be more sensitive to high X, and some experiments might be more sensitive to low X. You have some experiments which are sensitive to C quark asymmetries, for instance, U bar, D bar excesses, and things like this. I think that is something that we have more control over. Yeah.
Okay, I see. So so the follow-up short question is, does that mean like in global analysis, people just use all the data from all the experiments they have?
Yeah, that's a very active field of discussion in PDF language. Is some data don't may not make sense to use parton distribution functions purely because some data it might be uh, particularly within the factor the question is mainly of is your data within the factorization region and or are you contaminated by let's say higher twist effects um, or off-shellness for instance things that where the PDF language might not be applicable and so we usually implement like W and Q square cuts to try to mitigate these, but these are often not perfect, and it's still a study of it's still a question for ongoing research, definitely.
Okay, yeah, thank you.
Yes, yes, of course. And so we think about global phenomenological fits of parton distribution functions as building a robust picture of hadron structure. Because what we do is we try to touch every sector of the standard model. So, for instance, I show the data in which the CTEC fitting group is fitted against, and each one of these experiments that's shown touch all sectors of the standard model. Um, including electroweak precision experiments across all different X ranges and energy ranges. And so I like to think about PDFs as effectively mediating our knowledge or lack thereof of the fundamental interactions. And so PDFs effectively encompass our understanding of how well we know the standard model or where there may be room to add new physics into the standard model. And so the goal, more so than developing central PDFs, is actually understanding their uncertainties and how they arise from the experimental measurements and how that translation occurs. And so because PDFs, they touch all sectors of the standard model, and we're trying to find new ways of inserting new signatures of new physics, PDF uncertainties place actually very important limitations to the discovery reach of colliders and on the potential for new physics to be found. So one example I'm just showing, I was not involved in this study, but I feel like it's a really nice example, is something like neutrino scattering at very, very, very high energies. We're talking exascale energies, which are relevant for these neutrino telescope programs at something like IceCube. And you can see that as we go to very, very high energies, the uncertainty on the prediction of the cross section, which is mainly stemming from the PDF uncertainty, starts to balloon at close to 50%. And this is purely because of we're very much in the extrapolated region. We have no data there. And so our uncertainties explode and therefore our predictions explode. And this is purely stemming from our knowledge of the PDF uncertainty. So it's important for us to understand this PDF uncertainty at very, very high precision so we can sort of mitigate this extrapolation error. Also, something that's really relevant in the fitting world is the fact that the parton distribution functions are often fitted with an assumed functional form, some prior knowledge. And this creates a parameterization dependence on the parton distribution function. And it was studied in this CTEC paper here on the right on the effect of this parameterization dependence by spanning many different functional forms and fitting them to world data. And you can see you can get wildly drastic results in the extrapolation region. Not surprising, but it's something to keep in mind in that this parameterization dependence and exploring its effect on the PDF uncertainties and therefore implication for particle theory is very important. And so this is a multifaceted problem. It's spanning many, many different energy scales. It touches all aspects of the standard model and beyond. And so it's important for us to develop tools in which we can look at this picture in a sort of global idea. And so I like to think about this as sort of an aspirational goal of using foundation models and building foundation models for fundamental physics. And so I'm going to talk, this is where I get to my AI/ML section. So for the purposes of this talk, you can think about a foundation model as a shared embedding space, which is broadly pre-trained to a large spectrum of data and then used to perform specialized downstream tasks. So one can think about encompassing things like experimental, theoretical data, lattice QCD measurements, various different BSM scenarios, various UV complete models. Maybe you want to do EFT related studies. And the foundation model ingests this information, and then we can perform a whole series of tasks such as maybe classification, uncertainty quantification, anomaly detection, which I have a whole separate talk of, but that's not going to be what I'm going to talk about today. There's also the idea of maybe doing some global fitting. And so that's mainly what I'm going to talk about today, keeping in mind this aspirational message, but really focusing on a single non-foundational model that connects lattice QCD and global fits, which in the end can be part of such a robust picture and a robust study. So I like to think about global fits as sort of an inverse problem, and many interesting inverse problems are often ill-posed. And what I mean by this is these are problems where the forward mapping is well defined, but the inverse mapping is ill-defined. And the beauty of these inverse problems is that there's typically multiple solutions to them. So one can think of something like a Platonic example of a forward mapping where a light shines on a three-dimensional object and casts a shadow. This is well-defined forward mapping. I know how to go from 3D shape to shadow. That's fine. But what if instead all I have is the information about the shadow? And I want to say, well, what three-dimensional object casts that shadow? And the answer is that there's multiple shapes that do that. And so within the cast of this problem, there are multiple solutions that contribute to the final answer. And therefore, these multiple solutions are what contributes to our uncertainty. And this is something that we need to think very critically about. I hope this is reminding us of this parameterization dependence I've been discussing within the PDF world, because this is exactly what we're thinking of. And so what we're trying to do is develop tools which look at this, solving this inverse problem and looking for multiple solutions. So we do this through a very simple, probably very almost archaic seeming example with a variational autoencoder. But it's also a very powerful and robust tool, even still in this world of transformers and foundation models, for instance. Um, so generative AI algorithms give us the potential to generate many different replicas which resemble the multiple types of solutions one can that can occur in these types of problems. And so we use this variational autoencoder inverse mapper, which was developed by a group in Old Dominion University, headed by Yaohang Li and Manal Almain. And essentially, this looks like a very typical variational autoencoder. You have an encoder function and a decoder function, and you go to some latent space, which is constrained to look like a prior distribution, maybe a normal distribution that you choose. But the idea is you also have this extra pathway of information, which I call M here. And this M is constrained to look like some type of observable that you want to look at. And with this extra pathway of information, it combines with the latent space distribution through the decoder and gives you multiple different solutions. And so I can explain this through the language of a toy model, for a toy problem, for instance. So let's say you have y equals x squared, and we want to understand how to do the forward mapping, which is very easy. I give you -3 to +3 integers, and you know how to square them, and it gives you y, and that's fine. This forward mapping is very well defined, very simple. But what happens if I want to start with y and I want to go backwards and find the x's that give me that y? The problem is that this backward mapping is not so well defined. And this is because the sign information in the forward mapping is abstracted away. And so the question is how do we reconstruct that missing information that's abstracted in the forward mapping? And this is what the VAIM does. So if I take, for instance, this y equals x squared problem, and I pass x's ranging from negative integers to positive integers, let's say, and pass it through my encoder, then what ends up happening is this encoder has a very funny behavior because of this extra pathway of information in M. So M in this case is y. And as M starts looking more and more like x squared as we're training, then this pathway of information starts to only accept positive numbers. And so what ends up happening is that the information on the negative numbers has to be collected in this latent space Z. And so as we get the positive and negative numbers here and strictly positive observables here and pass them through our decoder, we can end up collecting all of the missing information that was abstracted away in the forward mapping. So it collects missing information. And we can then look at this missing information and reconstruct and interpret it and try to say, okay, what was abstracted away? And so the missing information in this case, y equals x squared, is the sign. And so this is manifested in this latent distribution. You can see that if I do a principal component analysis on the latent distribution, that I now have clusters centered at +1 and -1. And so we can interpret this as the reconstruction of the missing sign. And so as this is fed to the decoder, it can then reconstruct the multiple solutions. So this is very fascinating, very interesting. But it's a problem which has two solutions, and that may not always be the case that there is a fixed number of solutions. What happens if there's an infinite number of solutions? Can something like a VAIM show us the answer to this potential problem? And so we take something like x squared plus y squared equals 1. And in this case, we know that there's an infinite number of solutions for xy pairs that give us 1. And so when we feed this problem through the VAIM, you can see that we can reconstruct the unit circle within some uncertainty, of course. And then we inspect the latent distribution and we find something actually very fascinating. We find that the missing information is the radial component. You can see these concentric circles, and it's going out and increasing order radially. But we can also see a second distribution, which is the angular information about the unit circle. And so we can see that we can reconstruct this information and by doing some clever tricks with the latent space, interpret it in terms of the language that we're interested in. And so
So
now, oh yeah, go ahead.
one more question about the
Yeah.
previous slide. So why there's something empty in the
Yes.
like -1 -0.5 or something?
That's a very good question. So the reason it does that is because the chosen distribution of the prior was a flat distribution instead of something more circular. So there are different choices that one can make for this Z here.
Mhm.
And so the C could look like a normal distribution, but in this case, I chose a uniform distribution as just an example. And you can see that this uniform distribution does not bode well for this type of problem. But if I were to choose a normal distribution, this hole would not be there, for instance. So this is just a problem with the training, but the idea is still there.
I see. So that means the prior do affect some results.
It can definitely, and that is something still worth studying with this particular tool.
Okay, okay,
So
thank you.
something that we're investigating. Now, for this particular problem, we know that the geometry of the latent space is going to be more circular. So it would make sense to use something like a normal distribution. But for any type of other physics problem, typically we're going to be using uniform distributions, as they tend to be a little bit more flexible and expressive.
I see. Thank you.
Yeah. And so now we can think about using this VAIM with a physics problem, for instance. This is this PDF decoder project that you were mentioning, Jen. And so uh, the question then is, the question that we're trying to answer is actually a rather old question, which is reconstructing parton distributions from their integrated Mellon moments. So Mellon moments are integrals of the parton distribution function in the longitudinal momentum fraction x, and it's varying powers of x as well. And so the question is how many Mellon moments do we need to fully reconstruct the parton distribution function? In theory, if you want infinite precision, analytically, you would need to have an infinite number of moments to do the inverse Mellon transform. However, if we're looking at lattice QCD data, for instance, we can't generate an infinite number of moments. We can generate, I think the most is at least 5 before we start breaking down the signal. And even 5 has large uncertainties. So the question is can we, with limited information, reconstruct the PDF from its integral? And so we use this rather fancy architecture, which is just a ResNet architecture, which involves jump connections across various different layers. And this allows us to preserve gradients if we're using very, very complicated architectures, for instance. And now in the input, we have the parton distribution functions is X in my VAIM. And this pathway of information is going to contain the Mellon moments for this case. So exact same setup of the y equals x squared and also the x squared plus y squared equals 1, except now we're using slightly different architecture. Nothing has changed about the fundamental procedure. And this information here is now the integrated moment of the PDF. And what we find is something very interesting. So we started with a very fantastical world in which we have access to 32 Mellon moments from the lattice. This does not exist in reality, but we just wanted to start with something rather robust to start with, and then push it to see how low we can go. And the ultimate goal is to get from measured data the parton distribution function parameters themselves. And so you can see that we actually do very well in the reconstruction of the PDF, the true PDF as compared to the decoded PDF from the moments. But the true underlying uh, uh, beauty of this project came when we looked at the Pearson correlations from the latent distribution to the output. So the Pearson correlations are linear correlations between two variables. In this case, we chose them as the x dependence of the PDF and the various different moments. So for the case that I'm showing on the right, we looked at the d plus d bar combination of the parton distribution functions and compared them to the moments of the u plus u bar, u minus u bar, d plus d bar, and d minus d bar moments, and looked at the Pearson correlations across all of these. And so one would expect that the d plus PDF would only be correlated with the d plus moments because those are their integrals. And those are what's highlighted in green. And so you can see that in green, we are mostly non-zero. So that's great. Those correlations exist. It means our VAIM is learning those physics correlations. Now, the very big problem is everything else should be zero or consistent with zero within uncertainties. And the problem is that there's many examples highlighted in red which are inconsistent with zero. And so what this is telling me is that this VAIM is learning non-physical correlations because it has enough flexibility to move information around possibly where it's not supposed to. And so you can see these spurious correlations, and that these generative models effectively hide these spurious correlations. Because if I look at this D plus D bar PDF, it matches exactly with the true. So I would think that everything is working, and I may make the assumption then that this model is learning physics. And the problem is it's not. And so the question is um, do we care that it learns physics or not, or are we just trying to uh, satisfy someone's some error metric? And so these questions I think are important, maybe a little philosophical, but I think it's important when we're trying to interpret physics from machine learning algorithms. And what we also found is that when we constrained the latent distribution to be much smaller, that now these spurious correlations all of a sudden disappear. And we get just the correlations which are what we expect. And so this was very interesting. So this was a more realistic situation in which I had just a few melon moments per PDF flavor, something that's realistic to the lattice now. And so these constraints actually force the model to learn something physical in this instance. And finally, I just want to briefly mention a more recent project in which we applied this VAIM on another type of lattice QCD inverse problem. In this case, it's actually a very similar setup to what I just discussed, where we take a melon moment with respect to the PDF. But in this case, instead of an X-dependent kernel in the moment, there's a perturbative matching kernel which connects the light cone PDF, which is what we expect, with something calculable on the lattice. So the lattice cannot calculate light cone PDFs. They can only calculate Euclidean correlators, and therefore there has to be some assumption of going between the two. And this is an aspect of perturbation theory, which has been deeply discussed in the literature. I just show a few representative examples. And so we take this, what's called pseudo-Yaffe time distribution, and which form double ratios to sort of reduce lattice systematics, and match it with the light cone PDF. And then we ignore a lot of the next to leading order contributions and quark contributions, for instance. And so in this case, what we want to do is extract this gluon PDF, which I show here, this G of X, from this lattice calculated data, which is in blue. So the question is can we do that? And the answer is yes, we can actually do that. So what I do is we applied the VAIM in the exact same way I just showed you. And this time we're extracting the parameters of the parton distribution function, functional form and analytic functional form. And this is shown in gray here. And now this is compared to a whole bunch of other phenomenological fits, which is not necessarily a fair comparison because the VAIM is only trained on lattice data, whereas the phenomenological fits are trained on much more constraining experimental data with much smaller uncertainties. But you can see that everything is comparable, which is great, especially within the lattice region of validity, which is typically defined as 0.2 to 0.7. And I also show our relative uncertainties. And you can see that in the region of very large X, this is the region where lattice data becomes much more sensitive to the PDF than, let's say, the experimental data. Now, this is also still a question going forward, but this is just a preliminary study to get the ball rolling here. And then we perform some sort of closure test in which we compare it to the lattice data, and our results agree with an uncertainty for the specific regions of the lattice. Now, we also look at the Pearson correlation, which I showed you before, between the PDF and the moment. Now we're looking at the Pearson correlation between the PDF and the reduced pseudo-Yaffe time distribution. And you can see that there's relative pools at various different regions of X, but more importantly, what's interesting is that all of the Yaffe time distributions tend to cluster. And what this is telling me is that in these regions, that there is redundant information in these RPITTs. So really, this Yaffe time distribution seems to be only giving very little constraining power on the shape of the PDF. But maybe that's enough to constrain something at large X more so than the experimental data. And so we can look at, for instance, the latent distribution for this very simple parameterization. These are the PDF parameters, and you can see that there is some missing information being collected based off of this structure, which is seen in gamma and delta. And so the question then becomes is could we do something even more interesting by adding in maybe other observables in a simultaneous fit of the lattice and the experimental data. So that's still an open question, for instance. All right, so I'm going to conclude here by basically saying that what I've shown is an extraction of the of the gluon PDF from lattice QCD data using the reduced pseudo-Yaffe time distributions, and this is using this VAIM framework. Now, this is extensible to maybe higher dimensional quantum correlation functions, something like the generalized parton distribution functions, where the inverse problem gets even more complex. So the beauty of the VAIM is that it's an end-to-end framework, meaning it's agnostic to the physics in which you're training it on. So this becomes a very useful, powerful tool for possible theoretical discrimination between various different methodological descriptions of the data, for instance. And so these results open a generative AI-based pathway for embedding lattice QCD observables into global analyses. So this end-to-end framework makes this a nice way to do this. But that very careful care must be taken when one wants to quantify uncertainties. This is still a very open discussion in machine learning, is quantifying the uncertainty budget, separating aleatoric from epistemic uncertainties. So this is once again a whole talk on its own. And that this VAIM framework offers a convenient way for studying lattice information and assessing its implications on phenomenological studies. And this is something that we're currently working on. So yeah, thank you for your attention.
Thank you, Brandon.
Thank you, Brandon.
Yeah, so I think it's time for you guys to ask some questions. If you have some question, you can just unmute yourself and ask Brandon directly, and or you can just send some message, and I will read that for you.
Um,
Please
I
do.
think I have a question. So, how do we know that if we have enough physics information to feed the AI to obtain because you said the inverse mapping, the challenge is usually like it's not one to one, it's the one to multiple. Then how do we know the Poisson distribution we determine here is unique and totally follow the physics?
Yes,
And the would that also depend on the model parameterization?
yes, yeah. That's very good question. So, um, yeah, there's kind of three parts to that question. So, how do we know that we're obeying all the symmetries that we expect, maybe through baryon number conservation? So we want, for instance, the u minus u bar, the integral to be equal to one, to yeah, and so to two, sorry. And so the idea is well, these symmetries have to be enforced in the choice of the final PDFs. So we can't accept solutions that disobey theoretical constraints. Now the question is do we bake that into the architecture itself or not? For the choice of how we've trained, for instance, this model here, where we looked at the lattice reduced pseudo-Yapheton distributions, we only fed it examples which obeyed the symmetries that we expect. And with this VAIM, we would expect that the outputs then should also obey these final cuts. But we did check that, and the outcomes did only obey the theoretical constraints that we input into it. So that's good. So it's not giving us, you know, wildly very different solutions, for instance. And so yes, I think that was did I answer most of your question? Was there another part? I apologize.
Maybe you can correct my understanding. So right now this stage is more like to see if this AI model is self-consistent and
Yeah,
preserve all the physics information we give them.
that's exactly right. Yeah.
Okay, I see.
Yes, and there's various ways to do this as well. We just chose to do it in the particular way that I discussed, but one could think about other ways of enforcing, you know, potential standard model symmetries, for instance.
I see. Thank you.
Could I jump in on this slide?
Yeah.
Brendan, my name's Noah Breali. So I noticed this lattice validity region, 0.2 to 0.7. Jinshen's advisors worked a lot in this region. In lattice QCD, this is the focus. In your motivation slide, you showed these beautiful, spectacular, it's motivated by these spectacular neutrino telescope discoveries. This past February 2025, there was an exascale event in the detector that's in the Mediterranean. IceCube has seen these kind of events. In your motivation slide, you showed the uncertainty window was kind of blowing up outside this region of validity. It was blowing up kind of in the small x and the x close to 1 region.
Yeah.
And I wonder, I mean, from that motivation, right, we would really be interested in a new way of getting at that source of uncertainty from the small x region. You know, when these everything's moving very fast, but the fraction of the longitudinal momentum is going to zero, right? So that kind of region brings to mind what in condensed matter physics is called conformal invariance. When we look at the critical point of boiling water, you know, you put it under pressure, you reach this critical point. There's an emergent scale invariance that magically lifts on the light cone in 2 dimensions to a whole infinite dimensional conformal algebra, the Virasoro algebra. And in contrast to Jinshen's advisor, he says condensed matter physicists never work at the critical point. In fact, there's a whole ology that developed about 30, 40 years ago in the mid 80s to look at exactly this conformal limit and use that algebra to constrain 2-point functions in Euclidean time. It works in Euclidean time. And so I wonder why you restrict to this lattice QCD input if the main motivation is for the small x experiments where the uncertainty is really blowing up.
No, that's a great point. So the motivation is not necessarily to only investigate the small x, although that is really a really important region and potential some BSM modeling. For instance, if you have some neutrino scattering events at these very, very high energies, one could think about introducing very, very, very heavy new physics in these regions and potentially probing that. And that does scale to this very low X regions. But I think for the purposes of this study, this was mainly looking at understanding within the region of validity of the lattice, which in this case we took to be the large X region. Now there's also potentially new interesting physics in this large X region that one could think of. Also looking at possible higher twist effects and things like this. These occur at large X as well. Now, Yeah, I think my motivation is not necessarily only to probe the low X, but just to think about how to take this lattice data and map it onto the PDF phenomenology, for instance. And we know, for instance, that the PDF this lattice data, for instance, at the very low X, which is corresponding to these very large new these data are not going to be constraining the low X region, for instance. So yeah, so based off of this information and this RPITD method, we know that we cannot constrain the very low X with the statistics that we have, and the high X region is normed away through the construction of this reduced pseudo Yaffe time distribution. So we're kind of left with sort of this intermediate region, which seems to map to about 0.2 to 0.7. That's the main reason why I limited my discussion to this particular region. But yeah, one could also think about maybe, let's say, adding in this lattice data with experimental data, which is much more sensitive to the low X. One could think about then doing this, and that's actually something that we're very much interested in.
Can I also have another quick question? So, you showed us that you use this model on this pseudo PDF factorization. Um, I was wondering that if you use different, for example, like maybe LabMAT factorization or other model, do you need to retrain your AI model or?
Yes. So currently, the way the training works is that we have to have the PDF and its corresponding forward mapping. So right now we have that corresponding forward mapping for the for this Yaffe time distribution, but nothing's to say that we can't do the exact same thing with Lamette observables as well. And as I was mentioning in the end, the VAIM is model agnostic. It doesn't know anything about Lamette or Yaffe time distributions. Its only knowledge is what you give it. So if you give it both, you could find something very interesting on potential discriminating power between these two methodologies and starting to think about ways of resolving potential uh, uh, um, method of potential discrepancies or differences between different methodologies. So this is something that's also very interesting. So this isn't married to necessarily one particular lattice method. Currently it is, but that's just because that's how we trained it. But the methodology itself is not.
So I think my question now it's more like, so this AI model will also heavily depend on how we deal with the input. Like we need to understand like what's the application range for this uh, um this data we put in. For example, like Lame has its limitation, pseudo has its limitation, and how do we combine them? Like those stuff. The AI model will also like depend on those how we deal with input, right?
Yes, yes. So I think
Okay.
I think the yes, because the AI model will not this particular model will not tell you anything about the physics of Lamette or the physics of the pseudo distributions. You have to still obey those symmetries when you're constructing your training data. Now if you don't, and you can still construct data, that is an interesting question. Will it tell you, will it group particular solutions based off of, does it obey the particular physics we're interested in or not? I'm not sure in this latent distribution. That's definitely something to explore.
Let's see.
Maybe I can follow on that one. So melons are power laws, right? This scale invariance business, it's about predicting that power law. So could we put in some bias of the f of x encoder that it should be a power law at low x? And
Uh,
how would that affect if we inject that conformal invariance, that symmetry, that scale invariant symmetry? I wonder how that would affect our uncertainty budget at low X, the one that's relevant for experiment, obviously.
Yeah, so when we looked at this, I didn't put it in the slide, but effectively what the inputs are for this model is not the X dependence of the PDF itself, but actually the parameters. So we use an X to the alpha, 1 minus X to the beta, starting function, and then we put in a few extra parametric terms for gamma and delta. These follow a very similar uh, fitting functional form that one normally takes for a PDF as like a starting method, for instance. And so this X to the alpha is this Reggie-like behavior it does exist at low X for these distributions. Now the problem is that there's very little constraint on this alpha parameter, and one can actually see that a little bit uh, in this latent distribution. You can see that there's very little structure to this alpha parameter, unlike these analytic parameters gamma and delta, which enter in that parametric form in the functional form. So it has very little constraint on this alpha parameter. You can see it has some, which is very interesting, to say the least, that there is a little bit of constraining power on this X to the minus alpha term, but it's not enough to discount a huge uncertainty at low X.
Sorry, Brandon. So, for example, for the first plot of alpha, could you explain what does that mean on that, like, on these dots?
Yes. So essentially, what each of these dots are is well, what I do is I take alpha, beta, gamma, delta, and these are the parameters of my model, for instance. And then I plot this against the predicted, well, what's given in the red and blue are the values of the RPI of one of the RPITDs. These don't change very much between RPITDs. So that's the color. And you can see that there's no real structure in the correlation between the alpha parameter and the RPITD.
Yes.
So that's essentially what this is telling you, is it's kind of a different way of thinking about the correlations between these various different things.
Well,
So
Brent,
pretty.
isn't that what we would expect? These time distributions, Euclidean time distributions, pseudo-Yaffe, are just, they're coming from the lattice. The lattice tells us nothing about small x.
Exactly. So there it's giving us sort of what we would expect for this X to the minus alpha, for instance.
So this plot is a good motivation for a graduate student in a PDF group to use these conformal symmetries to calculate alpha with the same precision that these gamma and delta have been calculated in perturbation theory. This is non-perturbative, of course, using the conformal symmetries. Alpha is with what they call the conformal weight, the Virasoro algebra's conformal weights. They pop out of the representation theory. There's some tables for simple cases. For SU3, it's going to be harder.
Mhm. Yeah, I think so. I think I think there's a lot of continuous work to be done with these various different methods and incorporating them into more large scale fits, let's say.
So this is analytic, so it'd be fit free.
Right, yeah.
Okay, so previously I got a message from Shanlong. She has a question saying, is there any inherent symmetry with the PDF that is current model taking advantage of that? I think you partially mentioned that you use those symmetries, right? So what?
Yes. So yes, yeah, so we preserve the valence integral number, for instance. We also ensure, for instance, that if you take just random numbers between -1 and 1 for alpha, beta, gamma, delta, or whatever, whatever your constraints are, you can get Yaffe time distributions that span -1 to 1, for instance. But We know for a fact that these Yaffe time distributions are not going to cross zero. We know this from the data. So we don't take those particular inputs to train on. And so this is also another type of quote unquote maybe symmetry. It's just, it's not necessarily symmetry, but it's more just a theoretical constraint on the inputs that we don't want our model to be predicting things that are wildly non-physical, for instance.
So these symmetries are enforced strictly.
Yeah, well, it's not a construction of the architecture of the
Oh,
so no, it's not that the model cannot uh predict those. It's that the input training data is limited to not include examples of those.
I see. Yeah.
And therefore, as by construction, the outputs will be very, very unlikely to ever show those examples.
Okay, so do we have further question for Brendan?
I had just a hi Brendan. Cool talk. I just had a question about an earlier graph that you had, like I think it was on slide like 1 or 2, where there was just a whole bunch of like gridding to your data points, and I didn't know if there was any significance to I think you were talking about, yes, this one. So experimental data, and there's a whole bunch of structure on this graph on the right, and I didn't know if there was any particular way to quickly kind of understand what was happening.
Yes. So these are just a description of where the experimental data lie for something like deep and elastic scattering experiments or Drell-Yan experiments. And so they probe various regions of the Bjorken X dependence of the experiments, which is given in the x axis. And then also they're at various different scales, the perturbative scale, which is this Q. And so you can see that various different experiments touch varying regions of the total phase space, for instance.
But the particular, I mean, this is just a choice by whoever's running these to only probe these particular lines,
Yeah,
just
it's a
to like
choice.
saturatively.
Yeah, it's also dependent on, for instance, the initial scattering energy, the collider setup. Some of these are PP, some of these are EP experiments. So, for instance,
Uh,
PP, you're going to reach higher energies, you're going to go lower in X. Some are EP, and so you're going to be restricted to more higher X, for instance, or something like that.
The straight lines
cool. Yeah.
might reflect the Bjorken scaling. Like a fixed scattering angle or something, you get a linear relationship between Q and X.
Well, yeah,
Something.
yeah, but
Okay.
these are not the structure functions
Right.
measurements. These,
This is
yeah,
the structure function, the function of Q and X, and then you find this scaling relation that you only depend on X and with the Q power of Q out front. So this is the magic of the deep inelastic scattering from the 60s that we discovered quarks. So I think it might be these are fixed scattering angle for fixed target experiments in the old days.
right.
But some of these are
Mm.
collider data, so I don't know why they would plot it the same way, but kind of a beautiful plot.
Yeah. Cool. Thank you.
Yeah, of course.
Okay, so do we have further question?
Sorry, maybe just one more questions. So that I was wondering what's the future prospect for this AI model? Because you mentioned that right now it's you use the same model. Sorry, you use the model and then you can test that if this model learn in the physics. But then in the future, if this model they already learned this physics, can we go beyond the applicable range of the model we put in, or
Yeah, I think this model, I think this particular VAIM model certainly has its limitations and applicability. I don't know if necessarily this will find anything new about extrapolating beyond models, for instance, because I highly don't trust extrapolation and interpreting extrapolated predictions with AI ML. That's actually a whole separate branch of my research is uncertainty quantification, especially related to these extrapolated regions, for instance. But I think what's interesting and where I hope to see something like this going is related to kind of this grand vision of a foundation model, for instance. And if you are able to put in experimental data, theoretical data, lattice and BSM into some sort of and whatever else you want, whatever theoretical constraints, and passing them into a foundation model, for instance, and you put something like a VAIM on the output of something like a head on this. I think that's where I could see this heading is sort of like a nice generative head that can predict new and interesting potential solutions, given a whole bunch of input data that maybe encapsulates a variety of different theories.
I see. I see. Because the reason I have this question is like Lamed or the pseudo PDF that um, they have their own applicable range, but then they can already do this extracting the PDF with the lattice input. So I was wondering then what this model can do beyond this framework.
Yeah, I think what this model can do is actually serve as sort of a test bed for these two different frameworks. So these two different frameworks live within their own physics defined, applicability, for instance. But if you put them together in something like this model, which is possible because it's an end-to-end framework, it doesn't care about how you generated the data, as long as there is data. One could think about then using this model for as some sort of discriminatory power between these different methodologies. I think that would be very interesting.
I see. I see. Thank you.
Yeah, of course.
Okay, so due to the time limit, we already about 1 hour. So let's thank Brandon again. Yeah, thank you, Brandon. This is a nice talk. And probably I have some follow-up questions to you, and probably we can find opportunities to discuss that Argonne somewhere. Yeah. So
Yeah, absolutely.
stop recording now. Okay.